All right, physics. Here we go again. In this little mini lesson, I'm going to talk about what happens when we send an electric current through a magnetic field. Quick review of the last one. We made the startling revelation that magnetic fields come from the movement of electric charge. So it's not quite a fundamental thing. It's dependent on electric charge and it's dependent on it moving. And we introduced this right-hand rule to tell us about the shape of the magnetic field. You go ahead and grab that electrical wire, current carrying wire, and with your thumb pointing in the direction of the current, your fingers will wrap around the wire in the direction of the magnetic field. And we had this formula to give us the strength of that magnetic field. And it only depends on how strong the current is and how far away you are from the wire and some constant. If you're looking at the wires, as if you're looking through them, if the current is coming at you, remember we used that little dot to represent something coming at you, then that would be the case where you're holding your thumb and you're about to poke yourself in the eye with your thumb, and now your fingers wrap around in like this direction here. What do we call that? Counterclockwise, anti-clockwise. And if you do the opposite, if you have a wire carrying a current into the page, and for that you have to sort of distort your thumb and shove it away from yourself, and then your fingers will wrap clockwise. Sometimes we want to draw that same picture from a different angle, two-dimensionally, and that's where we have, so here I have a wire carrying a current upwards, and it's like that's how you would just give a standard thumbs up gesture to the screen, and now my fingers are pointing towards me to when I'm on the left of the wire over here. But if I curl my hand around, my fingers will be pointing into the page on this side. And so that's how we would draw the magnetic field, sort of two-dimensionally. We saw that if you had loops of wire, then those magnetic fields sort of team up inside the loop. That's another picture of the same basic idea. Inside the loop, the magnetic field created by the wire teams up. And that's a loop from another perspective, and you get these strong magnetic fields passing through a loop. But yeah, today's question is really about, all right, so magnetic fields are created around moving charges, around currents. So if that's the case, if electric currents produce a magnetic field around themselves, what's going to happen if I shove a current through an already existing magnetic field? What's going to happen to that wire, guys? What is going to happen to that wire when I switch on the current? Well, here's what you know. If you've got an external field and you've got a wire, so you know what external fields look like. Oh, look at me being tricky drawing on the screen. Show some respect. And you've got your current carrying wire making that circular magnetic field. If I shove that wire into the external field, those fields are going to interact in a weird way. I'm going to get this weird shape. And it's not obvious to me when I look at that field, okay, so what happens other than I've got a wacky looking field. But it turns out that the wire experiences a force, and that force is in, the force is down towards that sort of weak field location, away from the strong field. I don't quite get why, but and maybe there's a more causal explanation, or it might just be like a brute fact that, I don't know, the current moves downwards in this case. The way that those two fields interact, the wire itself is pushed downwards. It experiences a force. So in slow-mo, here we go. close the switch on this little circuit. Oh man, here comes some positive current. It's going to pass through that wire in the field. When that happens, there's a force. And the force in this case pushes it outwards. Now the external field would be here from north to south. Wow, that's some awesome scribble. So the field is upwards. The current from this perspective is into the page, and then the force is to the right. And this looks like a potential awesome equilibrium problem, by the way, where I've got like a force pushing it out that way, and of course I've got a tension force up that way, and a gravity force up that way. This diagram looks disgusting. Oh man, I wish I had a Surface Pro right now and I could do cool stuff. Have patience with me, kids. Anyway, big idea. Current in a field gets pushed. This is a real life one, and you can see a huge deflection there as that guy switches on the current. So the wire, he switches on the switch, massive, big deflection. Now, is this a big deal? Like, is this important? Heck yes, it's important. We can now turn electrical currents into kinetic energy. We can push wires around. This is a world-changing discovery. This allows electrical devices to become mechanical devices. So everyone who brushed their teeth with an electric toothbrush this morning, you have this force to thank for it. Anytime we have electricity creating movement, specifically in a motor, we have this to thank for it. And you just think of how much electric motors have revolutionized the world. So we've got a new force here, guys. And we usually ask this question when we introduce ourselves to a new force, like what factors would affect the size of that force? If you want to pause and see if you can predict, feel free. What would make this force big? What would make this force not so big? There are 4 factors that affect the size of this force. Obviously, the more current, oh my gosh, the more current that we have, the bigger the force. The more of the wire that's in the field, the bigger the force. So the length of the wire, that's an L, affects the size of the force. And obviously, the stronger the magnetic field, the more the current and the field interact. It turns out that also the angle between the current and the magnetic field also matter. I like this formula because I can pronounce it as Philby, and that sounds cool and cute. So I often call it the Philby force, but it's actually called the Lorentz force. So F equals ILB sine theta. And an important question is, okay, what direction does that force push? And here I get to introduce you to a really cool feature of your Year 12 physics experience, this cool gangster gesture that we need in order to find the direction of the force. There's 2 ways that you can find the direction of this force. One is with this gangster gesture where your pointer finger represents the direction of the field, your thumb is direction of the current, and then your middle finger is like the force. And it looks real ghetto and kind of, I don't know, cool. I actually don't like this one though, as cool as it is to have a gang sign. So I recommend not using this one. I recommend this style, which I'm going to call Eastside. So imagine Bruce Lee, and he's holding up his right hand there, and he's going to take the palm of his hand and he's just going to slam it into some guy's nose and kill them, whatever. Just like palm them in the face. That's what you need to think. So palm of the hand is the force. And then his fingers represent the field. And I like that because we often have lots of field lines. And you've got 4 fingers there to be your field. And fingers and field both start with F. And so it's nice and easy to remember. So fingers for field. My thumb does look like a wire. Like it's just this one lone thing. And then the palm of my hand is the force. So I like this one. Fingers for field. And that's what I'm going to use for the remainder of this lecture. Thumb for current, and then the palm of your hand, Bruce Lee style, is the force. So, cool. Yay. Let me get a better picture. This is my little practice session for you guys. So I've got 6 pictures here, and I want to see if you can put that right-hand rule. This is the second right-hand rule. So we have the right-hand rule, grab a wire, it shows you the magnetic field. This is the Lorentz force, right-hand rule. See if you can predict, I've got 6 wires here in 6 different magnetic fields. I want you to see if you can predict what direction the force will be. You should pause the video. See if you can predict all 6, and then I'm going to go through it. Alrighty. First one. So first I've got to figure out where's the field here. The field here would be from north to south. That's how we draw them. And so then how do I orient my hand? I'm going to put my fingers in the direction of the field and my thumb in the direction of the current. And so that, for you looking at the screen, should look like that. Your thumb is up, your fingers to the right, and your palm now is into the page, right? The force there, that wire would be deflected into the page. That's what we call that. How about this one? Well, I'm going to have to orient my fingers. Those are little crosses. Remember, that means arrows flying away from you. That's into the page. So orient my fingers into the page, and then I'm going to rotate my thumb around so that it points to the right. So I'm going to hold my hand kind of like that. And now my palm is facing upwards. The force is up. That one, yeah, so the field comes out of the north, away from the north, and the wire is going to the left. So I'm going to put my fingers down, my thumb to the left. So you should have your hand oriented like that. And now the palm is coming at us. So that's a force out of the page. Horseshoe magnet. Again, field goes from north to south. It would not look, there's obviously other field lines that we could draw. Right, that field would kind of bulge out, to be honest, like that. But whatever, I just need the field. Where the wire is. So I'm going to put my fingers to the right. That current is coming at me, and that's sort of an awkward place to hold your hand, but your palm should be facing upwards, kind of like that. Right, that's a force upwards. This one's dangerous. You're going to put your fingers to the right, and if you try right now to bend your thumb in the direction of the current, you're going to find that you would have to snap your thumb clean off to get it to point the opposite direction. That turns out to be significant. It turns out to be very significant indeed. The angle between your fingers and your thumb, the angle between those two matters for the size of this force. I didn't talk about this when I did the sine theta bit, sorry. So when your thumb and your fingers are at right angles, that is the maximum force. When your thumb gets pushed all the way down and is touching your fingers, there is no force. And in this scenario, if you have to pull your thumb all the way back, so there's 180 degrees between your finger and your thumb, that's also zero force. So although you would orient your hand like that, because you have to break your thumb to do it, there's 180 degrees between thumb and finger, no force. All right, last one. Fingers to the right. Current is into the page. So if thumb into the page, you should hold your hand like that, and force is down. So those were the answers. Hope you did all right. We actually use this force, this Philby force, to define the strength of a magnetic field. This is where the definition of 1 Tesla comes from. So shove, if you have a force of 1 Newton on a current on 1 meter of wire, you get 1 Tesla. Turns out we can also call a Tesla a Weber per meter squared. That's right, a Weber. I'll talk about what that means when we get up to what the heck flux is. I'm going to leave you, instead of with questions to do, with this tantalizing little picture. I think it'll be just easier to go into the next lecture rather than do questions at this point. That's an electron, and that little electron is flying into a magnetic field that's into the page. I wonder what it's going to do. See you in the next lecture.